all the stops to make this happen. Now, since the competition, since the concept design, the design has changed and it's different now. And we're going to show you some of the differences. We're also going to show you some of the tools that we used. One great thing, again, that is happening in our industry is engineers and architects have tools available to them that they did not have in the past. And these tools are very important for us to drive towards low-energy buildings. Tools like virtual environment, computational fluid dynamics software from Fluent, eQuest, Ecotech. And I should have mentioned Autodesk. I did not. I apologize. But all of these tools are extremely important to us because they allow us to design buildings in a very iterative way where we can look at how architectural and structural design changes will impact the amount of energy consumed by buildings in a very rapid way. When we look at how we design buildings right now, the largest of buildings, 3, 4, 5 million square foot buildings that will take years to build, sometimes it will take years to design. Most of the major decisions on these buildings are made in a month or two in concept design. So there is very little time to evaluate big picture decisions. And without these kind of tools, we cannot make the right decisions fast enough. So coming back to the wind. The way that the building uses wind, I think, is very unusual. We have not been able to find any other examples where buildings have attempted to pass wind through the body of a building in an effort to generate power. But we believe that it makes some sense to do so. Tall buildings inherently give us stronger winds. As you move above the ground, the wind speeds increase everywhere. This curve right here that you're seeing shows that natural effect of wind increasing in velocity as you rise above the ground. Another important thing to know is that when you look at power potential, the ability to generate power using the wind, there is a cube function between power and velocity, which means a very small increase in velocity can yield a very large increase in power potential. And that's what this second curve here shows. So in studying the building, we used wind tunnel testing. We used CFD modeling to study how we could use the wind to our advantage. We created these openings in the building, and there's 4 holes, 2 at this level, 2 at this level. We created these openings at the mechanical floors, and I think that's important to note because if you created the openings at non-mechanical floors, you would be giving up valuable leasable space. We were able to create the openings at the mechanical floors because of the type of mechanical systems that we chose for the building. The systems that we chose allowed us to put in smaller equipment, smaller handling units and fans, and it created extra space at the mechanical floor. So we created these openings, and the openings do a lot for us. Not only do they give us an opportunity to capture the wind, but they also reduce the pressure on the building created by the wind, and it saves us in concrete and steel. Looking at some of the testing, these charts right here show the effect of the wind. It shows 2 measurements. One, it shows velocity of the wind approaching a building, and the second number that it'll show you is the velocity of that wind as it passes through the hole in the building. The graph on the left will show what happens in one of the upper holes in the building, and the one on the bottom shows a lower hole in the building. So you see this circle. This represents the velocity of the air coming towards the building. What happens is we put the model on a lazy Susan in the wind tunnel, we take a measurement, and then we rotate the building 10 degrees. We take another measurement, and we spin the building all the way around until we have 360 degrees of measurement. So as you can expect, the velocity of the wind approaching the building doesn't change much as you rotate the building in the tunnel. This second graph shows the velocity of the air passing through the hole. And here you see that effect. You see this acceleration that is happening because of the positive and negative pressures that build up on the buildings. And on the upper holes, we see the air velocity doubling as it passes through the opening. And we see that happening when the wind is blowing from the north or when the wind is blowing from the south. And it doesn't necessarily seem to matter what the direct angle of that wind is, as long as it's hitting one of the long faces of the building. It is only when the wind hits the very side of the building that the velocity through the hole is less than the wind approaching the hole. But the winds in Guangzhou are fairly reliable in terms of the direction. They come from the due south for 10 months of the year and from the due north for 2 months of the year. So it is the only time that we would ever really expect strong winds to be hitting the side of the building would be during a typhoon. And we wouldn't want the wind hitting the turbines during a typhoon anyway, so it turns out to be a good thing for us. Now when we look at the lower opening, you see that the wind approaching the building is less. Again, because the lower openings are closer to the ground, the natural wind speeds are less. The surprise to us is what we measure in terms of the velocity of the wind through the openings. What we discovered is that it's not really the velocity of the wind approaching the building that impacts the velocity of the wind through the hole. It's this pressure differential. This blob right here is roughly the same shape as this blob, even though the velocities approaching the building are very different from one another. So for the openings that are lower in the building, the wind that is approaching the building will accelerate to 2.5 to 3 times the speed as it passes through the opening. But on average, we're looking at an increase in velocity through the hole of about 2 times. Now, where this is significant, again, power potential is the cube of velocity. So if you double the velocity, 2 times 2 times 2, the power that you can generate from these turbines increases by a factor of 8. So 4 turbines located in the building would be equivalent to 32 wind turbines sitting outside the building. Here's one of our CFD models, again showing this effect. This is showing pressures on the building. And the front side of the building, you see that bright red piece, very high pressures on the front of the building, and on the back side, very low pressures. This pressure differential is exaggerated because of the shaping of the building, the sharp corners on the side, the rounded top, and then by placing the holes in the building, those are our pressure relief valves. So if you have a nice 4 meter per second wind approaching the building, it can accelerate up to between 8 to 10 meters per second on average passing through the openings. And again, another CFD model showing this effect. See that red spark as the air passes through the building? CFD, computational fluid dynamic modeling. And there's a blow up of it. So that's one of our 32 strategies, and I won't go through all of them, but all of them are things that are not typically done in a conventional building. This is a picture of the wind turbine inside the opening. It's known as a vertical axis wind turbine. This particular one was manufactured by a company by the name of Quiet Revolution in the UK. And the client liked it. They liked it for a lot of reasons. They liked it because it is quiet. It has very low vibration, but they also liked the appearance of it. They thought it was very sculptural. And when we look at this one particular strategy paired up against all the other strategies in the building, the power generation is still relatively low, comparatively speaking. And as a matter of fact, at the end of schematic design, we had suggested to our client that he may want to remove the wind turbines from the building because they were performing a little bit less than we had hoped in our original calculations. And he said absolutely not. He said that one thing that was important to him in this building is that it communicate what it's doing to the outside world. So these wind turbines will give the building motion. They will give the building animation. As you drive by this building and you look over, you will clearly see that there's something different and unusual about what's happening in the building, and that is very important. And we're hoping that that will enable people to want to take a closer look and see the other 31 strategies in the building.
What is the name of the company that makes this wind turbine? It's called Quiet?
Quiet Revolution. So the wind turbines are located again on